Yes, class. Is this audible?
Good evening, ma'am.
Yes, ma'am.
Okay. So in the last class, we had completed with magnetic flux. Magnetic flux was B dot A. This we had seen. Faraday's laws of EMI we had seen. Laws of EMI were what? First law was that whenever change in magnetic flux is there, it will definitely produce induced EMF. And a continuation of that law, you can say, or you can say the second law of EMI that says that the induced EMF's magnitude is directly proportional to rate of change of magnetic flux. Now, when we wrote that formula, I had added this negative sign, remember, because of which we were getting this negative sign. This negative sign. So the formula was E is equal to minus d phi over dt. We talked about this, but this was left. Why we had minus sign? And I had told through the help of Lenz law, we'll be able to do this. So coming to Lenz law is an important topic. This is important. Directly questions can also come from here. And your theoretical questions mainly come from here. Numericals for Lenz law are rarely asked in your exam. So you should focus all your theory questions in EMI. These are oriented to your Lenz law firstly. Now, Lenz law says what? See, whenever there is a change in magnetic flux, it will change, it will increase or it will decrease. What will happen? Induced EMF will be produced, and induced EMF will thus produce induced current. Now, magnitude of this induced EMF will be what? This is given by E is equal to minus d phi over dt. Sorry, not minus. E is equal to d phi over dt. Here we are just talking about the magnitude, so we will not write it. So E is equal to d phi over dt. This is the magnitude. Now, what about the direction? What about the direction of this induced EMF? What about the direction of the induced current? So, direction of induced current is such that it opposes the cause that produces it. What produced induced EMF here? It was the change in magnetic flux that produced induced EMF. So, induced EMF's work is to oppose the cause. Now, cause can be anything, but here now we know what's the cause. What's the cause? It's either the change, increase or decrease in the magnetic flux. Fine. So induced current does what? Induced current, it opposes the direction of this induced current. It is in such a manner that it opposes the cause that produces it. For example, you can say magnetic flux is increasing. Number of magnetic field lines are increasing, magnetic flux got increased. When magnetic flux got increased, there was an induced EMF, which was higher induced EMF you were obtaining. And because of this induced EMF, you had an induced current. So when there is a change in this magnetic flux, induced EMF is produced and so the induced current. Now, when we talk about the direction of this induced current, it is in such a manner that it opposes the cause that produces it. So you can say it directly opposes the magnetic flux. If magnetic flux is increased, induced EMF will try to orient itself in such a manner that it will decrease magnetic flux. If the magnetic flux is decreasing, then induced current will try to arrange itself so that the current increases. Induced means the cause. Yes, induced means something that has been produced. Induced, induction, from the term induction. Try to recall, we have done induction in the first lesson also, methods of charging. So induced means you are inducing something. Here you are inducing EMF, means EMF has been now produced. Induced current has now been produced. Fine. So here direction of induced current will be in such a manner that it will oppose. Oppose means what? If the magnetic flux is increasing, induced current will set its direction in such a manner that the flux will decrease. Or if the flux is decreasing, induced current will set its direction in such a manner that the net flux gets increased. So yes, I have written these statements. Direction of induced current is such that it opposes the cause that produces it. That is the change in flux. This is the Lenz law. The statement is asked in the exam. And it is in accordance with conservation of energy. Please remember this point also. It is in conservation of energy. Now, let's take certain examples. When we were discussing magnetic dipoles, I have told you for determining the direction of current for south and north pole, for determining the current direction of current for south and north pole. For example, this is south pole. This is the direction of current for the south pole. This trick I have told you, draw S, put arrow, draw N, put arrow. That will give you the direction of current for the south polarity. Now what will happen? So this is how the polarities are developed. Now I have brought a bar magnet with north polarity over this side and south polarity over this side. And with certain velocity v, I am bringing this magnet closer to it. Now what will happen? Magnet is coming. So what's the cause of the magnetic flux or induced current will develop? A current will be set in there. So induced current's direction is to be in such a manner that it opposes the cause. Now, how can you oppose it? If north pole is coming to you, which polarity should be developed in the coil so that north pole is opposed? If you want to oppose north pole, which polarity you should develop in the coil? South or north? North. Yes, Priya. It has to be north polarity because north and north will only repel each other. No, for example, this is the coil, this is the bar magnet that is coming. So if this develops north polarity, this will get repelled. So north polarity will go back. That is what is the purpose of the Lenz law. You have to oppose the cause that is producing it. So if north pole is coming to you, the coil develops north polarity so that it opposes it. So what's the cause here? Cause is the north polarity. And how to oppose it? By developing north polarity. Now, if I ask you if a bar magnet is approaching towards a circular coil, what is the direction of induced current that should be developed? Just look here. This is how we write it for north. So this becomes, this is anti-clockwise. Anti-clockwise is the direction of the induced current. I induced. They will repel by opposing. They have to repel by opposing because the purpose of this is to oppose. Got it? Like this. So if the question is asked to write or draw the direction of the induced current for a coil if bar magnet of north polarity is approaching, so the coil will develop current in the anti-clockwise direction because the polarity that will be generated will be north. Reason? Because north pole will oppose the north pole, as Lenz law says that the induced current's direction is in such a manner that it opposes the cause that produces it. This is the way you will answer such questions, and these questions, these examples do come. Let's take some more examples. This is a bar magnet, north polarity, south polarity. Fine. This bar magnet is moving away. Now, what is happening? Bar magnet is moving away. It means flux is decreasing. Flux is decreasing. Now, what will induced current's direction will try to do? It will try to increase the flux. So, the purpose of induced current's direction is to increase the magnetic flux. If this is moving away, the only way to attract north pole is by developing south polarity. So, if it develops south polarity, it means if it develops current in the clockwise direction, then this bar magnet will come closer, magnetic field lines will increase, and magnetic flux will increase. How the flux decreases? Magnet is moving away. Magnetic field lines are moving away, so they are decreasing. If you bring magnetic field lines closer, if you bring the magnet closer, the number of magnetic field lines increases. So got it, Fahad? So the direction is clockwise. How are the number of magnetic field lines decreasing? Magnet is moving away. So number of magnetic field lines will decrease. If field lines are decreasing, it means flux is decreasing. Now Lenz's law will get applied and the purpose will be to increase the flux. This is happening. Purpose is to increase the flux. This is like the aim. To increase the purpose is to increase the flux. To increase the flux, you have to bring the magnet closer. So if you in any manner you want to bring the magnet closer, it's just by developing south polarity. Let's take some more examples. A bar magnet is approaching the circular coil with south polarity. All of you answer me in the chat box what should be the polarity developed by the, not the polarity, direction of induced current. Tell me the direction of induced current. Direction of induced current. All of you reply me in the chat box. South polarity is approaching. So direction of induced current. Only Priyadarshini has answered. Any answers? Induced current should be towards south. Induced current direction cannot be towards south or north. What did we study? Induced current direction is developed. Current's direction is developed with a polarity of coil. See, bar magnet, I am repeating one part give you, you have to try now. Otherwise, I'll start calling out names and I'll ask you. Bar magnet of south polarity is approaching. If bar magnet is approaching, it means magnetic field lines are increasing. Now, what's the aim? Aim of the induced current is to decrease the field line. How can the field lines be decreased? If the bar magnet is thrown away, if the bar magnet is repelled, then only the number of field lines can be decreased. So south polarity can be repelled by only south polarity. Now this is not your answer, Sahal, that south polarity is the direction of induced current. Yes, Priya, now you are right. It is clockwise. So south polarity is developed in the coil to oppose the approaching bar magnet so that number of magnetic field lines can decrease. Increasing, decreasing is correct or incorrect, or it's beneficial or it's harmful. That is not your concern. You just have to focus whether field lines are increasing, induced current will develop a direction opposite to it. Now you have decided that polarity will be south. Once you have decided the polarity will be south, what did I tell you? Just put arrows at the end. Now see what is the direction of current. It is clockwise. So this I was asking you, what was the direction of induced current? One more part I'm giving. This is south, north, bar magnet is moving away. Tell me direction of induced current, all of you. Otherwise, I'll call out names and I'll ask you to answer. Try this, it's easy, just with the steps that I've done. Direction of induced current. Fahad, answer. Abia. Okay. Sahal, tell me one thing. Sahal, if the bar magnet is moving away, what is happening to the magnetic flux? Is it increasing or decreasing?
Decreasing.
Magnetic flux is decreasing. Fine. And what will be the aim now? Sahal?
Aim would be to increase then, or
To increase the flux.
Okay, so it will be anti-clockwise.
Okay, okay, sir. Fahad, if magnetic flux is to increase, then to bring the bar magnet closer, should the polarity be south or north? Fahad. Aziz.
South.
South will bring south to itself. How will you look at the figure, Fahad, on the screen? If this is the bar magnet, because this is only lens law and questions do come from this, just pay attention. If bar magnet is moving away, means south polarity is moving away. How will you attract the south polarity? Fahad? Yes, Fahad.
Yes, ma'am.
How is south polarity attracted? Okay, tell me one thing, Fahad. South and north attract each other? North and north or south and south? Like attract each other or unlike attract each other?
South attract north.
So south attracts north. So
And
if south
repels.
south repels. So if south is moving away, to attract it, what should be the polarity?
North.
North. Got it, Fahad? Why will it be north?
Yes, ma'am. Got it.
Okay. North polarity. Fine. Abia, now can you answer what is the direction of current? Everything is now written. Abia?
Anti-clockwise.
Anti-clockwise. So this is just a trick. North and south, you can directly answer also. So direction of induced current will be anti-clockwise. I hope now it is clear. Let's see one more thing. This is where coil question comes. This. All right. Now, this is a rectangular coil. It is coming inside it. Fine. This is coming inside. So it was outside earlier. This rectangular coil is coming inside. These are all magnetic field lines present. Rifat, you tell me, if this coil is coming inside the magnetic field, So will the flux increase or decrease? This is coming inside this region. Will the magnetic increase? Yes, definitely. Because magnetic field lines are increasing, so magnetic flux will increase. Now induced current's purpose is to what? To decrease it somehow, because magnetic field lines are increasing. So now the aim of induced current will be somehow decrease the flux. Fine. Now see class, understand this part one, I'll give you and I'll ask you. Now what will happen? Now our aim is to decrease the flux somehow. So the net magnetic field line that should be developed should be lesser. Then only no flux will decrease. If somehow magnetic field lines, induced magnetic field is pointing inwards and original magnetic field is also inwards, understand this class carefully. There will be one induced magnetic field also. So if the induced magnetic field is pointing inwards and these original magnetic field lines are also pointing inwards, the resultant magnetic field will be induced magnetic field plus the original magnetic field. Means that is all, one is already pointing inwards and the other induced will also be inwards, then the net magnetic field will be what? It will be greater magnetic field. Greater magnetic field will lead to greater amount of flux. See opposite. If here the original's magnetic field direction is what? Inside, inwards. If magnetic induced magnetic field is in a manner, if the induced magnetic field is outwards, this is outwards. So what will be the net? Outwards, inwards, both will get subtracted and it will result in decrease of magnetic field. And therefore the magnetic flux will also decrease. First understand this point, then we'll relate. Magnetic field lines, if they are pointing, the induced magnetic field lines and the original magnetic field lines that are present, if both of these are pointing in the same direction, be it inwards, be it outwards, wherever, in this example it is inwards, no, in any case it can be in any manner. So if magnetic field lines are pointing to, it's like two vectors. If two vectors are pointing in the same direction, resultant is always greater. But if two vectors are pointing in opposite direction, making an angle of 180 degree or any angle greater than 90 degree, then the resultant is always lesser. Simple logic of vectors. So if magnetic field lines are, if both are outside, then also it will increase. You should not focus whether it's inside or outside. Focus on the fact whether they are in the same direction or in the opposite direction. They can be in the same direction outside, they can be in the same direction inwards, they can be in the same direction rightwards, they can be in the same direction leftwards, upwards, downwards, anywhere. You should focus on the fact that if magnetic field lines are in the same direction, it will increase the magnetic field. And whenever magnetic field will increase, magnetic flux will increase. Now, if in any direction, in any of the path you choose, they are pointing opposite to each other. Induced is inwards, or original is outwards, induced is upwards, original is downwards. In any case, you can say when both are in opposite direction, whether one is right, other is left, one is up, other is down, resultant will be what? Lesser, because net magnetic field will be what? You will subtract. When both of them were pointing in the same direction, you added the fields. So you got a net increment in the field. Now what is happening? Magnetic field lines are pointing opposite. When magnetic field lines are pointing opposite to each other, what will happen? Resultant magnetic field will decrease. So if net magnetic field is decreasing, magnetic flux will also decrease. Got this point? Now I relate to you what we are studying. Just understand, you have to focus whether magnetic field lines are pointing in the same direction or magnetic field lines are pointing in the opposite direction. If you see magnetic field lines, not only about magnetic field lines, it's about the vectors also. Two forces are which are pointing in the same direction. One force is 5 Newton, other force is 3 Newton. Both are pointing in the same direction, let's say right. The net resultant will be what? 8 Newtons, you will say. But had it been one pointing towards the right, other towards the left, using sign convention, you will get the resultant as 2 Newton. Because when two things are opposite in vectors, you have studied this. Got this point? Now see, This coil is coming, this first coil is coming into this. So as rightly answered by Rifat, magnetic flux will increase because the amount of magnetic field lines that are getting enclosed within this loop will also increase. If magnetic flux is increasing, now induced current, according to Lenz's law, work of induced current is just to oppose this. Somehow it has to decrease the magnetic flux because it cannot tolerate the increment in the flux. It has to decrease the magnetic flux. That is the purpose of induced current now because of Lenz's law. Lenz's law is this, that law exists, so this will happen. Now, remember for circular and any closed loop, I have told you, curl your finger along the sense of current. Thumb gives you the direction of magnetic field. If current is going clockwise, anti-clockwise, curl your fingers clockwise, thumb will point somewhere. If fingers are pointing clockwise, point the thumb. The way we have done this. So here also, now what is happened? Which will I choose? Magnetic field increase or decrease? Obviously, induced current will try to decrease the field. And what did we study just now? Whenever you have to decrease the field, you have to choose the induced magnetic field in opposite direction. Got it? Now magnetic field is pointing inwards, the original magnetic field, and induced magnetic field has to point outwards. Then only both will get subtracted and a resultant decrement will be there in the net magnetic field. So if the magnetic field is pointing outwards, then if I curl my fingers, I'm able to see my fingers are curling anti-clockwise. It means direction of induced magnetic field will be outwards, and direction, if magnetic field is outwards, then curl your finger, this is anti-clockwise. So this becomes the direction of the induced current. This way you have to answer. A whole set of NCERT question is there in this, and it has been repeated in your examinations also. A question like this. Lens law questions are direct and simple. या तो वो coil वाला आएगा, otherwise this will be included. So whatever is there, according to the question, you have to answer. I am repeating this once. One part I'll give you, all of you should try. Any doubts I'll repeat because this is important and this is Lens law. Lens law will be over by now. Now Lens law will be over. This is the last thing in Lens law. We'll start with motional EMF. That's why I'm saying pay a little attention over here. First point, if magnetic field lines are pointing in the same direction, net magnetic field will increase. If magnetic field lines are pointing in opposite direction, net magnetic field will decrease. Magnetic field decreases, flux decreases, field increases, flux increases. Here in the first figure, when the rectangular loop from outside region was coming in the interior region, it was enclosing larger number of field lines. So more number of field lines came, higher will be the amount of flux. Now the induced current has to such its direction in such a way that it opposes the cause. Cause is increase in flux. It wants to now decrease the flux, and flux can only be decreased if magnetic field lines are in opposite direction. If one is inwards, opposite will be outwards. If you keep your thumb outwards, see the curling of your fingers, that gives you anti-clockwise. This way the direction was decided for the loop. Clear or not? 3 to 4 times I think I have repeated the same thing. I hope it's clear to all of you. Yes, no, any doubt? You want me to repeat what? Abia, Fahad, Madiha, got it? Rifat, Sahal, Priya, Samia. Understood? Okay. Now this is moving outwards. This second loop is moving away of induced current. Try this. Same step, same things. I'm waiting for your answer. Every child should try to answer. Even if it is wrong, I will correct you. This class direction only. No, don't write everything, Fahad. That I agree with you. Net magnetic flux. Okay, Priya has answered. Tell me the direction. Samia has answered. Both of you are correct, Priya and Samia. Others also try to answer. It will be either clockwise or anti-clockwise. See what's your answer. Yes, Sahal, that will occur. Net magnetic, that will occur to the net magnetic field. So what will happen to the direction of induced current? See, Rifat, just check once again. Fahad, correct? Correct, Fahad. Okay, Rifat, tell me one thing. Rifat Amna, you tell me, is the magnetic flux increasing or decreasing? Yes, Samia. Samia, the answer is yes to your question. Rifat, is the magnetic, yes?
Increasing.
See, the rectangular loop is now moving away from the region of magnetic field.
Yes, understood.
So it will decrease. Got it, Rifat? Here what had happened, this loop was coming inside, so maximum number of field lines were enclosing, so flux increased. Here it is moving away. All right, so that's why it is leaving the field lines and is moving to the exterior. So here the flux is decreasing. Now, as asked by you also, we have to increase it. We have to, not we exactly, direction of induced current has to be set in such a direction that it increases. It's Sahal, you are right. Correct. Okay. Now, Abia, you tell me, should the one original magnetic field is pointing inwards. Abia, you tell me, should the induced magnetic field be inwards or outwards? Just tell me this. Our aim is to increase magnetic flux. Abia. Hmm?
Inward.
Inwards, exactly. Then only both will point in the same direction and it will get added. So induced magnetic field direction will also be inwards because we have to increase it. No, it is decreasing. Flux is decreasing. We have to increase it now because of Lenz's law. So induced current's direction you have obtained. Now you have already obtained the direction of induced current. You just have to. Madhya, can you answer what should be the direction of the loop now? If the induced magnetic field has to point inwards, keep your thumb inwards. See the curvature of your finger. Madhya, keep your right hand thumb inwards. See curling of your fingers. Are the fingers going clockwise or the fingers going anti-clockwise? Yes, Madhya, it is clockwise. See, keep your thumb like this. This is inwards, curling of finger. This is what? Can you see? Clockwise. This is what? This is clockwise. This will be, keep your thumb inwards, curling of finger will be clockwise. So direction of induced current will be clockwise. All right. Now, Abhi, is it clear the direction?
Yes, ma'am.
I hope it's clear not only to Abhi, others also. Rifat, Sahal, Priya, all of you had answered correctly. So that was about your Lenz law. Note it down, note down all the points. Whichever point you're not able to understand, ask me. I'll explain it again. That was your Lenz law, and questions will also come like this only. V is some random velocity that I've taken. It's just to depict that the bar magnet is in motion. Nothing. Just velocity to depict that bar magnet is moving. See, Fahad, for the induced current, no. Induced current's direction, you have understood till the fact will the magnetic field be pointing inwards or outwards? That you've understood. Are you able to decide this? Whether magnetic field, okay. See, if you have a clockwise coil, curl your fingers in the direction of current. Thumb gives you the direction of magnetic field. That we have already studied. Just opposite to it. If your magnetic field is, let's say, pointing outwards, keep your thumb outwards. See the curling of your fingers. This is pointing in the clockwise direction. Can you notice this? This is pointing in the clockwise direction. So this will give you clockwise. If, let's say, the magnetic field lines are pointing outwards, so I'll keep the thumb outwards, curling finger. This is giving me anti-clockwise. Like this you have to decide. Got it? Written. And others also? Okay, all of you have written. If anybody is writing, stop me. Otherwise, let's start with motional EMF. So that was your Lenz's law. In the red and green color, I've just written the statements that I've told you. Can we start with motional EMF now? See, emotional EMF is also nothing. This is not a tough topic. EMF, no, once you have understood. That's why I was constantly saying, till chapter 4, you have to build your basics. After chapter 4, it's just the combination of what you have studied. So EMF we have already studied. If EMF occurs in motion, if EMF occurs in such a conductor that is in motion or that is moving, that EMF we call it as motional EMF. The way induced EMF was also the same EMF. It was just because it was produced because of change of magnetic flux, we named it as induced EMF. Here also the EMF is produced because of the motion of the conductor. We say it's motional EMF. Nothing changed. It's a very easy topic. This lesson is very easy. You can find alternating current a bit difficult and more tougher than this. But this lesson, this is a very easy scoring lesson. And topics are also small. I think hopefully by the next class we should be able to cover this lesson. So I have chosen a U-shaped conductor. This U-shaped tubes, not a tube exactly, iron supports I have chosen. And this PQ you are able to observe, no, this PQ. PQ. This is a conductor whose length is L, and this conductor is moving. It's like this is the support of iron supports that I have taken, and I'm sliding the conductor like this. Got it? Exactly like this. This is the conductor. This is the conductor PQ, and this is that yellow U-shaped supports I have shown. This is like PZ, and this is sliding. I'm able to slide it. So this is PQ. I'm able to slide it, and length of this conductor is L, which is moving with velocity V in this. Got it? X is this distance. This distance is known as X. X is basically the length of the loop that is present inside. Now, magnetic field exists everywhere. Magnetic field is present. Yellow lines are just iron supports. How will you move a conductor in magnetic field? You need certain supports, no? So they are just like, they are acting aluminium supports you can take. Just U-shaped supports are there. Okay. Main function is done by the conductor and the magnetic field lines. And magnetic field lines already exist, which are pointing inside. Flux is what? Flux is magnetic field line into area. Magnetic flux, not electric flux. Magnetic flux is magnetic field lines into area. And area of this will be what? Length multiplied by breadth. Area of a rectangle is what? Length into breadth. Length is L. The area that is left within is X. So phi is what? Phi is B L X. EMF, using your Faraday's laws of, this is a derivation. Using Faraday's laws of EMI, you can write the magnitude of EMF as what? D phi over dt. Put the value of phi, that becomes d BLX over dt. Magnetic field is a constant, it will come out. Length of the conductor will always remain fixed, it will be L. But this small x is variable. You can see here the x value is very less, here the x value is greater. X is variable, so it has to be differentiated. Now dx over dt, all of us know from very lower classes as well, dx over dt is nothing but velocity. So formula of motional EMF is BL, simple. First it is EMF is BL. This is your motional. Formula is easy, B multiplied by L multiplied by V. Got it? One more thing I forgot to mention when we were discussing Lenz's law. E was equal to minus d phi over dt. So this negative sign, now you can relate with it. Why is it Lenz's law? Because direction of induced EMF is in such a way that it opposes the magnetic flux. That's why we put a negative sign to depict this. I forgot to remind you again, but we have discussed, everything is same. The whole theory remains the same over here. Got it? So your motional EMF is what? Motional EMF will be, this will be E or V, this will be equal to BLV. This is the potential difference or EMF you can say. B is the magnetic field. L is the length of conductor. and V is the velocity. Right? This is your motional EMF. Induced current is the opposite of magnetic field. Oh, see, induced current's direction with magnetic field is not concerned directly. What I have told you, direction of magnetic field you have to specify. If magnetic field lines are pointing inwards, somehow magnetic field lines are pointing inwards, then direction of induced current will be clockwise. So opposite to magnetic field is no relation with it. There's no relation between induced current and magnetic field. Induced current and magnetic field lines have no relation, as in clockwise and anti-clockwise I'm referring to. Current can be clockwise or anti-clockwise. Here magnetic field is what? Inwards or outwards, like this. Got it, Fahad? Just put your thumb in the direction of magnetic field, right, left, wherever, and curl your fingers. If it is towards the right, curl your fingers. This is the direction of induced current. Wherever is your induced magnetic field line that you want to generate, put your thumb in that direction. Okay, this is motional EMF. Now one or two modifications of this formula that come, then we'll do the numericals. Current is equal to E divided by R. So EMF is what? BLV. So current will be BLV divided by R. Force is equal to BIL. Force for a conductor, for a single conductor, we did it was BIL. In the last to last lesson we have done that. So magnetic field is B. Current from here, right? Current from here, BLV by R. This is current, BIL. What is the formula we are getting? B square L square B divided by R. Power is force multiplied by velocity. What is force? B square L square B divided by R multiplied by velocity. This is force into velocity. So force into velocity, that becomes B square L square B square divided by R. Got it? This was emotionally a very small topic. Now a major topic that is left from this lesson is induction, self-induction and mutual induction. Those are also not difficult. In the second one there should be I. Here, Fahad. BIL, force formula BIL. Okay. See, Fahad, force's formula is BIL. Just check. BIL. So current is what? BLV by R. This is I. BIL. Got it? Fahad. It's not. Yes, it's the conductor. PQ is the conductor whose length is L. EMF that we have already studied, same EMF, electromotive force, that is the maximum potential or maximum voltage that is applied across the resistors, maximum value of the voltage.
Ma'am, the V in the first after the first equality sign velocity, right?
V here, BLV, that is the velocity.
No, that is velocity, and the first V.
That is the potential. EMF or the potential. This is the potential.
Ma'am, is there any units for the EMF?
EMF's unit is volt. Voltage, it's voltage.
Voltage itself.
Yes, it will.
Got it.
See, this question says what an aircraft with a wingspan of 40 meter flies with a speed of 1080 kilometer per hour in the eastward direction at a constant altitude in the northern hemisphere, where the vertical component of magnetic field is 1.75 into 10 to the power minus 5 Tesla. You have to find out the EMF. Formula based question, direct formula based question. See, length of the conductor here, this wingspan is acting, the wingspan of the aircraft is acting as like the length of the conductor. So length is what? Length is 40 meters. Speed is 1080. So we have to convert it into meter per second, 5 by 18. That will be 300 meter per second. Just check it's 300 or not. And magnetic field is what? 1.75 into 10 to the power minus 5 Tesla. What's the formula of EMF? EMF that will develop will be VLB. This will be 1.75 into 10 to the power minus 5 into 40 into 300. Whatever that you'll solve this much. Simple. And there is no difference that will come because of it. How 5 by 80? Whenever you convert kilometer to into R, you multiply it by 5 by 18. Because 1 kilometer has how many meters? It is 1 kilometer is made of 1,000 meters, and 1 hour has how much seconds? 3,600 seconds. So that is 60 minutes multiplied by 60 seconds. So once you cancel this, that is 5 by 18. So whenever you have to convert any meter, kilometer per hour into meter per second, just multiply it by 5 by 18. Note this question, note down the solution, just text me done, then I'll stop. Okay, the answer is coming 0.21 volts. Okay, okay. Thank you, Priya. Just text done in the chat column when you've written. Okay, then. So I think most of you have completed it. All those who have written, you all can leave. One more topic is left, induction, that we'll do in the next class. Thank you so much.
Thanks, ma'am. Allah Hafiz.
Thank you, ma'am.
21,000. Just check with the zeros. I think some 10 to the power minus 5 is also there, no? Just check with it. So final answer will be 0.21. You are near the answer only, Fahad. Just check the zeros once.